We've touched on molecular polarity a little bit. We talked about polarity of bonds. So covalent bonds can be classified as either polar or nonpolar, depending on the difference or lack thereof in the electronegativities of the bonded atoms. Polarity also applies to molecules as a whole. So it says electron density may be higher on one side of a molecule than another due to one of two things. One, the geometry of the particle, so how the atoms are arranged around the central atom. And secondly, the polarity of the individual bonds. Number two primarily applies to a situation where you have a molecule that's made of two total atoms. And the polarity of that covalent bond then will be the same as the polarity of the molecule as a whole. Again, just a reminder, dipole moments symbolized with the lowercase Greek letter mu that is, just like with micro. It's the product of the partial charges and the distance by which they are separated. Again, not super important. You just need to know that dipole moment is a way of quantifying the polarity of a bond or polarity of a molecule. All right, so molecules will be polar to some degree if they have different atoms attached to the central atom in a molecule, or if there are lone pairs of electrons on the central atom. Now be careful, there's a couple exceptions, molecules that have a lone pair of electrons on the central atom but are nonpolar. So one of them is AX2E3, that's a derivative of the trigonal bipyramidal geometry. This type of molecule would have a linear geometric shape or linear molecular geometry. And so that, even though there's lone pairs of electrons on the central atom, those electrons each cancel each other out, giving rise to a nonpolar molecule. The other exception is a derivative of the octahedral electron geometry, AX4E2. The molecular geometry for this type of molecule is square planar. Again, those lone pair of electrons in the axial positions cancel each other out, again giving rise to a nonpolar molecule. So just like we did with molecular geometries, let's go back in the notes and look at our Lewis structures that we've already drawn and identify each of those molecules as polar or nonpolar. All right, so let's start with carbon tetrafluoride, CF4. And if you want in your notes, you can just write the chemical formula, or again, go back to the pages where you drew these Lewis structures and label them if you have room. Something else that we look at is what I call symmetry. A symmetrical molecule will be nonpolar. Now, by symmetrical, I don't mean in the sense of geometry where it's the same on both sides. Here's what a symmetrical molecule is. It contains, if everything attached to the central atom is the same, then that molecule is symmetrical. And if it's symmetrical, it is nonpolar. So let's take a look at this one, CF4. So what exactly is attached to the central atom? You have 4 fluorines. That molecule is symmetrical. Therefore, CF4 is nonpolar. Let me add to this. Let me draw another one that's similar to this. That's a little bit different and goes back to one of the things in the notes that we just wrote down. What if we had something like this, CH3F? So now the tendency for some students is to say, to make this generalization, that all tetrahedral molecules are nonpolar. Well, that's not the case here. So what exactly is attached to the central atom? We have 3 hydrogens and 1 fluorine. If you use the word "and" when describing what's attached to the central atom, that molecule is not symmetrical, and it is likely to be polar unless it's one of the exceptions we just talked about a minute ago. So this molecule is not symmetrical, therefore it is polar. All right, NCl3, what's attached to the central atom? 3 chlorines and a lone pair of electrons. So we're going to count that lone pair there. So because this molecule is not symmetrical, it is polar. H2S, 2 hydrogens and 2 lone pairs. H2S is polar. So here's what I was talking about before with the bonds. We have fluorine. Fluorine has just 1 bond in that molecule. If the one and only covalent bond in a molecule is nonpolar, then that molecule as a whole is nonpolar. So in this case, the bond is nonpolar, so F2 is a nonpolar molecule. What if it were this? Also a linear molecule. This time, the one and only bond in that molecule is polar. Therefore, this molecule HF would also be polar. Next, HCN. Attached to the central atom, you have a hydrogen and a nitrogen. This molecule is polar. O2, nonpolar. AlCl3, symmetrical molecule, nonpolar. SCl6, symmetrical molecule, nonpolar. We don't do polarities for polyatomic ions. It's only for molecules, so we're not going to label NH4+. SO3, 3 oxygens attached to the central atom, nonpolar. BEF2, 2 fluorines attached to the central atom. This is symmetrical, nonpolar. This one here, C2H6, is actually nonpolar. If you have a hydrocarbon that has just all hydrogens attached to the carbons, then it's going to be nonpolar. If there are some oxygens there along with hydrogens, then it could be polar. Xenon tetrachloride, we have 4 chlorines and 2 lone pairs, except this is one of the exceptions. This molecule is square planar, and it is nonpolar. IF3, 3 fluorines and 2 lone pairs. This is not one of those exceptions. This is polar. So again, hopefully you got all those. Rewind as needed. All right, next up we have multiple bonds, multiple covalent bonds. We're talking about double and triple bonds. So it says the first bond between any 2 atoms is always a sigma bond, it's called. So we use a lowercase Greek letter sigma to represent that, sigma bond. Whereas the second bond in a double bond, or the second and third bonds in a triple bond in a molecular polyatomic ion, form from unhybridized p orbitals. So let's back up a little bit for a second here. Sigma bonds results from the overlapping of 2 hybrid orbitals, or the overlap of 1 hybrid orbital and 1 atomic orbital. I'll show you an example of this in a little bit. The second and third bonds in a molecular polyatomic ion, where you have a double or triple bond, those form from the overlapping of unhybridized p orbitals. So remember we talked about sometimes there are p orbitals that are left unhybridized. Well, sometimes those orbitals overlap with p orbitals from other atoms to form the second and third bond in a molecule. Again, I'll show you what I mean with that by that in just a minute. All right, let's take a look at this molecule, C2H4. Let's draw the Lewis structure. This does have a double bond. So I mentioned this the other day. Anytime you're drawing Lewis structures, you want to draw them as accurately as possible. Again, showing the geometry around the central atom, or in this case, showing the geometry around each of the carbons. So each carbon has a trigonal planar geometry. Why does each carbon have a trigonal planar geometry? We've talked about this before, so see if you can think ahead a little bit. All right, next step. Let's take a look at the orbital diagram for the valence shell of carbon. Go ahead and pause the video, draw the orbital diagram for the valence shell of carbon. All right, so here's carbon's orbital diagram. Now again, going back to carbon being trigonal planar, why does carbon have a trigonal planar geometry? What does that say about the hybridization of each carbon? So each carbon in this molecule is sp2 hybridized. So let's draw the hybrid orbitals in our orbital diagram. So of course there are 3 sp2 hybrid orbitals that form, but carbon has 4 valence electrons. So there is another valence electron. Where does it go? Well, only 2 of the p orbitals combine with the s to give rise to the 3 sp2 hybrid orbitals, and 1 of the 2 p orbitals is left unhybridized. And that unhybridized 2p orbital has 1 electron in it. Something else to mention. we see here that and this will be true for each carbon has 3 hybrid orbitals. Hybrid orbitals are used in the formation of sigma bonds. So each carbon can form 3 sigma bonds. And again, I'll show you how in just a second. If you take a look in your book on pages 317 and 318, there's something similar as what I have here in the notes. It shows when you take the s and p orbitals and combine them to make the 3 new sp2 hybrid orbitals. So in the notes, those hybrid orbitals are shown in, I guess that's a peach color. And then the green are the unhybridized p orbitals. So when we have this molecule C2H4, the sp2 hybrid orbital here overlaps with the other carbon's sp2 hybrid orbital, and we can see that forms one of these sigma bonds. There's also a sigma bond that forms between the other 2 sp2 hybrid orbitals and hydrogen's 1s atomic orbital. So in this molecule, we have a total of 5 sigma bonds. Again, resulting from the overlap of hybrid orbitals with other hybrid orbitals, as is the case of the bond between the carbons, or hybrid orbitals and atomic orbitals, as is the case in the bonds between carbon and those 4 hydrogens. Now, if we look at the bottom left there, we see that the unhybridized p orbitals are perpendicular to the plane of the other bonds, these sigma bonds. And so if we go to the right there, we see that those p orbitals can overlap. Overlapping of 2 unhybridized p orbitals is known as a pi bond. And so in this molecule, we have 5 sigma bonds and 1 pi bond. So though it overlaps both above and below the plane of these sigma bonds, that's considered one bond. That is 1 pi bond. So let's fill that out in the notes. Again, reference those pages. It shows it very nicely. A little different colors than the ones I've shown here. The multiple bond, in this case the pi bond, as we'll see, is formed by the sideways overlap of unhybridized p orbitals. So p orbital from one atom, p orbital from another atom, they overlap both above and below the plane of the sigma bond, and these are known as pi bonds. It says electron density is high in pi regions because of the shape of the p orbitals. Their dumbbell shape allows for the overlap both above and below the plane of the sigma bonds. As it says here, the pi regions are above and below, being 180 degrees apart, the axis or plane of the sigma bond between the carbons. It should be noted that the unhybridized p orbital is higher in energy than the hybridized orbitals, so it's favorable for an atom to form hybrid orbitals. Sometimes, though, it does not form hybrid orbitals. Again, we can see this on page 317. All right, let's look at an example of the formation of a triple bond between atoms. Go ahead and pause the video and draw the Lewis structure for C2H2. How many sigma, how many pi bonds in this molecule? Just by looking at the total number of bonds. Go ahead and pause the video and write that out to the right of the Lewis structure. The number of total sigma bonds and the number of pi bonds. So we have 3 sigma, 2 pi bonds. If you're not sure where those came from, you'll see that as we go through the rest of this lesson. All right, next step. Before we get to the orbital diagram, notice the geometry around each carbon. What is the geometry around each carbon in this molecule? Each carbon is linear. Again, why is each carbon linear? has to do with the hybridization of the central atom. So let's once again look at the orbital diagram for carbon. It's valence shell only. Go ahead and pause while you do that. To have a linear geometry, each carbon must be sp hybridized. So one of carbon's p orbitals combines with its s orbital to give rise to two new hybrid orbitals called sp hybrid orbitals. But again, we see that carbon has 4 valence electrons, has 2 other p orbitals that do not combine with the s orbitals. Those are our unhybridized p orbitals. So again, we got 2 hybrid orbitals that carbon can use to form sigma bonds. Has 2 unhybridized p orbitals that are half filled with electrons, which can be used to make the pi bonds. Let's take a look at what that looks like. We see something similar on page 319. Again, different colors, same idea. So each carbon is sp hybridized. So we see that with the peach colored orbitals. So we have a sigma bond between the 2 carbons, overlapping of their sp hybrid orbitals. And we have sigma bonds between the sp hybrid orbital of carbon and the hydrogen. One on the left, one on the right. Now we have 2 unhybridized p orbitals, so shown in pink and in blue. Not sure if I agree with how they're shown here. It's kind of hard to tell. Remember, these p orbitals are perpendicular to one another. So p orbitals lie along the x, y, and z axes. So let's say that one of them that was used to combine with the s was along the x-axis. So now we have one along the y and the z. The orbitals along the y-axis will overlap, and the orbitals along the z-axis will overlap, giving rise to 2 pi bonds. And again, this is maybe a little bit more clear in your book to see. It's kind of hard to show 3-dimensionally overlapping both above and below the plane of the sigma bond, as well as in front of and behind the plane of the sigma bond. I believe that's what it says next in our notes. So it says electron density is high on the axis between the nuclei, that's our sigma bond, and both above and below the sigma bond, the first pi bond, and to the sides, in front of or behind if you want, the sigma bond, which is our second pi bond. Now something that's important, not all atoms can form pi bonds. It says due to the fact that pi bonds involve overlapping of unhybridized p orbitals, the atoms involved in the bond must be small. Those p orbitals must be close enough to overlap, and they're only close enough if the atoms that are bonded together are small. If the atoms are large, we're talking about unhybridized p orbitals in the valence shell. If they're in a high energy level, those p orbitals won't be able to overlap, and you won't be able to form pi bonds. Consequently, the only atoms that are able to do this are nitrogen, oxygen, and carbon. All 3 of those atoms have their valence electrons in the second energy level. They're all pretty small atoms. They can form pi bonds. Likewise, sulfur and phosphorus can also form pi bonds if they are bonded to either nitrogen or oxygen or carbon. 2 sulfurs bonded to each other, no pi bonds. Those unhybridized p orbitals can't get close enough to overlap. 2 phosphorus atoms, again, those atoms are too big for the unhybridized p orbitals to overlap. All right, so that concludes not only this unit, but this lesson. Congratulations. Thanks for watching.